Okay, so this is higher order implicit differentiation. This is part 2 of section 2.5. First thing you need to do is pull out your syllabus, and instead of problem 64, do problem 46. That's the first thing. Okay, so let's take a look. There are really two skills you're going to need to talk about in here. The first is how to do this higher order implicit differentiation. You remember this is the one where when we had y squared, it took the derivative, it was 2y dy dx. So now, and that gives us the first derivative, so we're going to find higher order derivatives, which basically involves then taking the derivative of this guy right here. Okay, before they do that, the first skill you're going to need to talk about is what are called orthogonal functions. So orthogonality is basically sort of a generalization of perpendicular. Remember we talked about several times perpendicular lines are ones where their slopes are negative reciprocals. So an orthogonal function then are basically functions, orthogonal functions, where the tangent lines are perpendicular. All right? Remember when we talked about tangent lines, the slope of the tangent is the derivative So what this means then is that orthogonal functions have derivatives which are negative reciprocals. And for those of you who don't remember what a negative reciprocal is, if you have 2/3, the negative reciprocal, you flip them, so it becomes 3/2, and then you change the sign. Or if you have negative 1/4, you flip them, it becomes 4, and you change the sign. Okay, so orthogonal functions. And why do we care about what they are? Well, there are a couple of things orthogonal functions come out of pretty regularly. Let's look at a couple of examples. Now, if you're rolling a ball down a hill, what you know is it's going to take the steepest and shortest path. So if we draw a contour map where it's 10, this is 8, 6, and 4. When we start something out here and we push it downhill, what we know is it's going to take the shortest path between here and the next one. but it's also going to end up being perpendicular to it. And then the same thing here, it's going to come down here, and then it's going to come down here. And what you'll notice is that these things always end up perpendicular to these tangent lines. So these can be used to find the shortest path of an object going downhill. You'll also see this if you look at weather maps. And they have isobars, which are lines of equal pressure. So the way the Weather Service basically predicts wind speed and direction is they're going to use these orthogonal functions. So if you have an isobar, which looks like this, what we know is the closer the bars are together, the faster the wind speed is going to be. And this again are these orthogonal functions. You're perpendicular to the tangent line. All right, your path will be perpendicular to the tangent line. And that gives you the direction the wind's going to blow. And you know that it will be blowing harder here than it will be here because these isobars are closer together. So you have a higher wind speed here than you have here. And so this is what you're doing is you're finding to prove two. So to prove two functions are orthogonal, find the derivatives. Oftentimes you're going to be evaluating them at a point. But even if you don't, you may or may not be doing this. If the derivatives are negative reciprocals, they're orthogonal. So let's take a look at an example. I'm not going to work through all of one for you, but we'll take one. Let's say we've got two functions f and g. F prime we found out was 2x squared. G prime we found out was 1 over negative 1 over 2x squared. Now what you notice is that these are reciprocals of each other. They've got opposite signs. That means these are orthogonal. And they're orthogonal for all values of x. However, let's say we have h prime was 1 over x cubed. K prime was x cubed. These are not orthogonal because while these are reciprocals, you notice that the signs are the same. So these are not orthogonal. Okay, so the last skill then we're going to talk about is higher order derivatives. And let's go back. Remember, add problem 46, delete problem 64. So let's go back and take a look at an old friend we did last time. And we want to find the second derivative. and y is a function of x, which means we have to do implicit differentiation. Okay, well, we've done this once already, but let's do it again. That's 2x power rule plus 2y power rule, dy dx, chain rule, equals 0. 2y dy dx equals negative 2x. I'm solving for dy dx. dy dx, then we divide everything by 2y, was negative x over y, because they cancel each other out. The 2's divide out into 1. Okay, so now let's take a look at the second one. So what I need to do is find my second derivative. If you remember from before, what we do now is we need to take the derivative of this. So the first thing I need to do is rewrite this as negative x, y to the negative 1. All right. Product rule. Now you can, if you want, leave it like this and do quotient rule. However, in this case, I think it's going to be a lot easier to go ahead and do product rule. Either way, it will get you the same thing. So f equals negative x, g equals y to the negative 1, f prime equals negative 1, g prime equals negative y to the negative 2 dy dx. So what I've got then is f prime g, so I'm going to have negative y to the negative 1 plus I've got a negative times a negative, so that makes it a positive. X, y, y to the negative 2, dy dx. Now you notice I've got a dy dx over here. We had solved that up above. Well, we know dy dx equals negative x over y. So I substitute that back in up here, and I'm going to end up with d squared y over dx squared will be equal to negative 1 over y plus, and then I've got x over y squared from here times a negative x over y. That will be negative 1 over y plus x times x gives me x squared. And I've got a negative, let's go change that to negative, over y cubed. And there would be your second derivative. Now you can come in so that if you did product rule, it would give you something very similar. This algebraically would be similar, it just would be in a slightly different form. Well, let's go ahead and do, while we're here, let's do quotient rule on this. So what we know, I'm going to skip to where we'd already done this. And I'm going to do quotient rule. So f is negative x. You don't have to put that negative with the x, you can put it with the y, it doesn't matter. I just chose to put it with the x. g equals y. All right, so f prime is -1. G prime equals dy dx. And so now I'm going to have f prime g, that will be -y minus f g prime negative, so that's going to end up being a plus x dy dx. Okay. And then I come back in and I substitute back in for this. We'll have -y plus x times -x over y. And that will give me -y minus x squared over y. Now these things look different, but they're not. If we go back and compare them, all right, it's easy enough to get to this one. If I multiply everything in here by y squared, it will get me this thing there. Excuse me, divide by. That's what I forgot to do. Because quotient rule now, we have to divide by y squared. Forgot about that. It's over g squared. So what I've got then is I'm going to have -y over y squared and then minus x squared over y times y squared. And that will give me -1 over y, I'm going to simplify that, minus x squared over y cubed. And we get the same idea that we did. Which one to use? It's a wash on this one. It doesn't really particularly matter whether you use product or quotient rule. Obviously, as you can see, it's real easy to make a mistake in remembering to come back in here and divide everything that I had. Because their quotient rule, if you remember, is f prime g minus g prime f over g squared. And I forgot to divide by g squared, which is y squared over here. And when you do, you get the same idea. It can be a little touchy in this case because of fractions and remembering to break these up. But either way you do it, it will get you the same answer.